Welcome back to the 3n+1 conjecture. So far, we've been looking for a loop to disprove the 3n+1 conjecture that all numbers go to 1. Now we're going to shift to proving that there are no 3n+1 loops, except for 1, 2, 1. We're going to start by trying to show that no circuit loops exist. That's a special kind of loop where we go up and up and up and then down and down and down with no extra gyrations. So later we can go back to considering whether any kind of loops exist. Here's a circuit of length 5, k equals 5, that starts with 3 up moves, x equals 3. So what's the bottom member of this loop, m? Well, we can use the 3n+1 computer to calculate it by pushing all the 3n+1 operations to the beginning of the operation sequence, then calculate beta, and divide by 2 to the k minus 3 to the x. Now in this case, beta involves multiplying strictly increasing powers of 2 by decreasing powers of 3, which is shown here. And in this case, 19 over 5 is not an integer. Now for circuit loops, beta amazingly simplifies to 3 to the x minus 2 to the x. So for example, this whole beta here simplifies to just 3 to the 6th minus 2 to the 6th. And here's an even simpler example. For 3 cubed minus 2 cubed, I'm going to start with this 3 by 3 by 3 Rubik's Cube and subtract out a black 2 by 2 by 2 cube. That leaves us with 3 squared in pink plus 3 times 2 in orange plus 2 times 2 in green. Houdini used this same trick when he went over the Niagara Falls in 1921. Anyway, if m is an integer, then we have a valid circuit loop. And that's only if this is a multiple of that. So now if 3 to the x minus 2 to the x were a random number, then the chance of that would be 1 over 2 to the k minus 3 to the x. In other words, we'd only have one arrow to shoot at that divisibility target. But last time we resolved to put aside all these childish probabilities and be adults. So we want to prove beyond a shadow of a doubt that 3 to the x minus 2 to the x is never a multiple of 2 to the k minus 3 to the x for any k in x. So let's make a chart of all the possible circuits in the universe. We select the number of up moves here and the number of down moves here. And in each cell, we're going to write down 2 to the k minus 3 to the x, the denominator. So for the circuit of 3 up moves followed by 2 down moves, we have 2 to the 5th, because k is the up plus down, minus 3 cubed, so that equals 5. Hey, pretty low divisibility target. And over here, we're going to write 3 to the x minus 2 to the x, which actually applies to this whole row x. Since 19 is not a multiple of 5, we're going to put a red cube here, meaning this is not a valid circuit. And if we can put a red cube on every circuit in this entire infinite grid, then we'll have proved that no circuit loops exist. So let's start with the first cell way up here. 1 up move followed by 1 down move. So 1 divided by 1 is an integer. So we found a valid circuit loop. It's 1, 2, 1. So let's put a green cube there. Next we have negative 1. 5 over negative 1 is also an integer, so we found another valid circuit, negative 5, negative 7, negative 10, negative 5. That's all the valid circuits we know about, so we want to red cube the rest of this chart. How about this one? 2 ups followed by 2 downs. 2 to the k minus 3 to the x is 7, which is not a multiple of 5. And here are a bunch more beta values. So let's see, is 65 a multiple of 47? No. Is 211 a multiple of 13? Maybe. Man, there's an infinite number of cells here, so going one by one would take forever. What we need is a general argument that'll take out an infinite number of circuits. So I can think of 3 arguments. First, if this number is smaller than this number, it'll never be a multiple of it. So we can rule out all these circuits, for example. This entire row. Second, if this number is prime, then we can rule out all the circuits on this row also. How? So 211 is prime, so it's only a multiple of 1 and 211. Gersonides already taught us that 1's never going to appear anywhere on this row or in this chart. And it's easy to see that 211 will also never appear in this row either. So we can red cube this whole row too. So this is very helpful, but in the big picture, not too many rows are going to have a prime 3 to the x minus 2 to the x. So our third trick is to play with the factors. So I'm going to replace all these numbers with their prime factors. Like 55 is 5 times 11, and 65 is 5 times 13. And I'm going to put a white cube now wherever there's a factor of 5. it's a very regular pattern. So notice that whenever x is odd, 3 to the x minus 2 to the x is not a multiple of 5. But on those rows, there are many values that are multiples of 5. And you can't be a multiple of 5 without having a factor of 5. So that means none of these circuits on these rows are valid integer circuits. So we can replace the white cubes with red cubes. And we've actually crossed out 1/8 of all possible circuits throughout all infinity with that trick. So that's 1/8 of a proof that there are no 3n+1 circuit loops. So that's pretty awesome progress. So in the next episode, let's shoot for the rest of the proof. Okay, see you next time.